Welcome to the Shape of Space lecture on least squares. In this lesson, we explore the concept of solving overdetermined linear systems, i.e. systems with more equations than unknowns, by minimizing the sum of the squared errors in the equations, and I'll get to what that means in a minute. This is known as the least squares method. The approach has broad applications across many fields. The technique was independently developed by mathematicians Carl Friedrich Gauss and Adrien Marie Legendre in the 19th century. So getting to the specifics, assume that we are given a tall m by n matrix A, where tall means m is greater than n. Let x be an n by 1 column vector and b be an m by 1 column vector. In this case, the system of linear equations ax equals b is overdetermined. The system of equations ax equals b has a solution only when b is a linear combination of the columns of A. Otherwise, we don't have a solution. And in fact, that's the case we want to look at, where we don't have an exact solution. But we do have a methodology to get something close, or hopefully close, to a solution. And what we do is we define this vector E equals ax minus b, and we want to find x to minimize this difference when we take this norm that I've shown down here. We just take E times its transpose, inner product, and you want to find x to minimize that inner product. This is known as the Frobenius norm. So the rest of the lesson is going to be about finding this x in different situations, and I'll also give you a few examples. The problem of finding a vector, which we'll call x hat, that minimizes this Frobenius norm is known as the least squares problem and is denoted by minimize this Frobenius norm. The input data for the problem are the matrix A and the column vector B. The quantity to be minimized is known as the objective function. Any vector x hat satisfying this inequality for all other x is a solution to the least squares problem. So this leaves open the possibility of having multiple x hats that give you a minimum value for this norm. Such a vector is known as a least squares approximate solution to x equals b. It is important to know that a x hat does not equal b unless, as noted earlier, b is a linear combination of the columns of A. The least squares problem can be cast in terms of the columns of A. And I'm going to give you a reference on a video I had done earlier concerning writing AX, where A is a matrix and X is a vector, is writing that in terms of a linear combination of the columns. You may not have seen that before. I'm going to use it just below here, but you may want to have a look at my video on that topic. So I'll put a link to that in the references to this video. So if C1, C2, let me point to these. If C1, C2, up to Cn are the columns of A, then the least squares problem can be viewed as finding a linear combination of column vectors that is closest to B. So this is what I was mentioning just a minute ago. So AX can be written like this, where these C's are the columns of A, and we want to find this linear combination that minimizes this norm here. If x hat equals these elements here is the solution of the least squares problem, then A times x hat equals this is the closest vector to B among all linear combinations of the column vectors of A. A row-based interpretation of the problem is also possible. In this case, we let R1, R2 up to R sub m be the rows of A. The components of the residual vector E equal this here. In this interpretation, the least squares problem is to find x that minimizes this function here. So this is in terms of rows, this is in terms of columns, and these different row and column representations are mentioned in my video, which again I'll give you a link to that. So if you're not familiar with this, have a look at my prior video. To reiterate, our problem is to minimize the objective function f of x equals the residual times its transpose, which in turn equals this expression here, on the assumption A is of full rank, that is, the columns of A are linearly independent. So we'll use the product rule to differentiate f of x, keeping in mind we have vectors here, so we need to keep the order intact. So we have the first times the derivative of the second term, then the derivative of the first times the second. Now keep in mind these are scalars because you have a vector times its transpose, so you're just going to get a scalar. And with that, the implication there is that the transpose of a scalar is just itself. So we can write this as its transpose, and then that is just the transpose of this is the same as this, and we get 2 times this here. And again, this is a scalar, so we want to get this transpose out of the derivative part, the differential part. So this equals its transpose. We have this here. And then finally, E is AX minus B. So derivative of this, A is a constant, so it's just A dx. So we get this being the derivative, and the minimum is achieved when the derivative equals 0 in this case. So it's when 2E transpose A equals 0, or we can divide the 2 out. And so we have this here. Then E transpose is the transpose of this, so it's X transpose A transpose minus B transpose. Remember, the transpose of a product is the product of the transpose. That's why we got this here. And then we have this. We take it to the other side. We're almost done. Then we multiply both sides by the inverse of A transpose A, and we get this here. And so this is our solution. I guess this is more of a side fact, but I'll mention it here. This is known as the Moore-Penrose pseudo-inverse. You don't really need to know that name, but what you need to remember is this is the solution. But in any event, I did a video on this, or at least where this is part of the video, and I'll give you a reference to that in case you're interested. Okay, so this is the most straightforward approach to solving the least squares minimization problem. You get a nice closed form here. Compute this, and then you would compute the inverse of this, and then multiply and get your answer. However, for large size matrices, this is not the most efficient solution. So I have another approach on the next slide that's more efficient, at least for larger matrices. So we have a different solution on this slide that's more efficient for larger matrices in terms of finding the least squares solution. It involves something called the QR decomposition of a matrix, and I defined it up here. I also have a video on this. I'll give you the link to that in the description to this video. So any real square matrix A may be decomposed as follows: Q times R, where Q is an orthogonal matrix. In other words, its transpose equals its inverse, and R is an upper triangular matrix. So that's what we want to do with the solution we found on the previous slide. Under our assumption that the columns of A are linearly independent, it's a known fact that the QR decomposition of A exists. So we'll write A as suggested up here, and then we'll take our solution, the Moore-Penrose inverse. This is what we found on the last slide. And then we're going to just plug in A here. So we have A transpose, so it's R transpose, Q transpose, and plug in A. Then take the transpose again. We write it all out. You get a lot of, given that the Q inverse equals Q transpose, you get a lot of cancellation. Well, these cancel. Of course, this is the inverse of each other. So these cancel. You just get the identity here, and that leaves us with this here. And again, since Q inverse equals Q transpose, and Q transpose is easier to calculate than Q inverse, we'll plug that in here. So that's our Moore-Penrose inverse in a different format, and then we use that to compute our solution. So we can write our least square solution in this form here, and then there's 3 steps in order to solve this for x. First, we compute the QR factorization, and there's a lot of known software and algorithms to do that. And then we break this into 2 parts. First, we compute Q transpose times B. That's fairly easy, right? It's just a multiplication. And then we take the R on the other side here, and then we solve this equation for x. This is known as a back substitution, and that gives us our least square solution. Okay, so that's the more efficient way. On the next slide, I'm going to show you the more straightforward way, just computing this Moore-Penrose inverse in a particular example. Before I get to the example, actually, I wanted to do a comparison of the 2 different methods, the QR method and the pseudo-inverse method. So we use something called big O notation. I'll give you a reference to this, but it's just basically counting the number of operations that are involved. So here's the comparison. Both methods provide the same unique solution when A is a full column rank. In other words, when the columns are independent. When A is rank deficient, in other words, the columns are dependent, the pseudo-inverse gives the minimum norm least square solution, while the QR method can be adapted via column pivoting to handle rank deficiency. In terms of numerical stability, QR decomposition is numerically stable because it avoids forming A transpose A, which can square the condition number of A. This is the condition number of a matrix measures how sensitive the solution of a linear system, AX equals B, is to small changes in A or B. So that's the definition of this term here. The pseudo-inverse approach, what's this solution here, can be unstable for ill-conditioned A due to the inversion of A transpose A. Computational cost, computing, and this is for the pseudo-inverse, computing A transpose A is of order m n squared, roughly this number of operations given the size of matrix A. Inverting is n cubed, so these are both roughly cubic number of operations. And multiplying is just square, so this is not a factor. The QR decomposition computing QR is mn squared, so that's similar to this. You don't have the n cubed thing in here, but solving Rx equals Q transpose B is order n squared. So these two are about the same. This is about the same, and then you have this little bit additional thing here for the A transpose A. So this makes this more computational intensive. For large M, both methods are dominated by this term here, but QR is more accurate. In terms of implementation, as we saw, the pseudo-inverse is straightforward. For smaller matrices, you can just go ahead and do the computations. For larger matrices, QR decomposition is more involved, but is the method of choice in many numerical libraries. Okay, so now let's look at an example. So let's look at an example. We have A equals this tall matrix. You notice we used the term tall earlier. So it's got more rows than columns. It's not real tall, but slightly taller than it is wide. And then we have our vector B. So first we probably want to check that the columns of A are linearly independent. So we can do some column operations here. I took A and then I subtracted the first column from the second, and I got this, and then I subtracted the second column from the first. And you notice you have a 1 here and a 0 here and a 1 here, but a 0 here. So there's no way of writing this in terms of that or vice versa. So we know the two columns are independent. So we should expect to get a unique solution. We want to determine the value of x such that this Frobenius norm is at a minimum. We use the pseudo-inverse method. So we compute A transpose A, which I've done here, and then A transpose B. So some simple multiplications. And then we solve, actually we don't just directly compute the pseudo-inverse, we solve this system of equations, which is equivalent to solving for the pseudo-inverse. And so we have this, these are the coefficients for x, and then this, of course, is 5 and 11. I'll spare you the details of this, but if you solve this 2x2 system, you get x1 equals 2/3, x2 equals 1/2. You can plug that into here. This is, remember, this is our residual E that we defined earlier. So we plug that in here, and then we get this solution for x. And then we can also compute what is the actual minimum here for this Frobenius norm. And we plug this into the, I mean, it's just a matter of multiplying this times its transpose. So you get 1/6 squared minus 1/3 squared, and then 1/6 squared. So you get 1/6. So that's the smallest value that you can get. For all the possible values of x that you could pick, this is as close as you can get to actually finding a solution to that systems of equations. You're off by 1/6 in terms of this norm. We can extend the least squares problem if we take x to be a matrix rather than a vector, i.e. let x be an n by k matrix. The new problem is to minimize ax minus b, so b is also a matrix here. So we want to minimize this Frobenius norm where all three of these things are matrices. A is m by n, b is m by k. If we express ax minus b in terms of corresponding column vectors, then the problem reduces to this form here where x sub j is column j of x and b sub j is column j of b. So this equals this, but then this reduces to the previous problem that we did. The objective function of the more general problem is just the sum of k instances of the initial problem with x and b vectors. Right now in this form here, x and b are vectors. We have k such problems. So we can solve each component problem separately, minimizing this in each case. And based on our previous work, we know that solution is x sub j equals the Moore-Penrose inverse times b sub j. And then we can just put all those column vectors together, the solution, to construct our matrix X. And then we can plug in these, so shown here. Then we can factor out the pseudo-inverse. And then what is this? Well, these are just the columns of B. So X, the matrix, equals the pseudo-inverse times the matrix B. Looks almost exactly like the format of the simpler case that we solved earlier. The least squares model is the fundamental framework used in simple data fitting problems where you have n input variables and one output variable. And I'm going to go through a little bit of the background here, then I'll show you an example. In terms of problem setup, there are m data points, observations, each with n input features. These can be represented as rows in a matrix A, so where each row corresponds to an observation. So this is one observation. This is another. And each one of these columns is a different feature or aspect of the problem you're studying. And these ones here are known as the intercept or bias term. This is kind of like where you have a baseline. Maybe you're looking for the price of you're trying to figure out the price of a house, and these are the different features that, it has a nice bathroom, it has a patio and so forth. So these are adding to the value, and then this is used to capture the baseline. So maybe if it doesn't have any of these particular features in a given neighborhood, maybe the baseline is 150,000. So these ones here are used is the what's called the intercept bias, and the actual intercept bias is this value x0, which I'll get to in a second. So yeah, as I say here, the first column accounts for the intercept bias term in linear regression, the value of the dependent variable when all the independent variables, in other words, all these are 0 for a given observation. Then the corresponding output is in a vector B. So using our house example, if you had this observation here with these different features in the house, then B1 would kind of be the resulting price from that observation. The model parameters, weights, are represented by the vector here, x. That's multiplied times a, as you might expect. We're kind of building up to this ax equals b. The key point here is that the linear relationship is assumed among the inputs and outputs. In other words, b is approximately equal to a times x, and x is the minimum solution to our least squares problem here was the Frobenius norm, which we already know how to solve for. So let's put this into practice and look at a particular example. So once we compute x, our solution to the least squares problem, we can use x to model some function from n-dimensional space to the real numbers that takes as input some vector d and provides an approximate output. So you put in this input and you get an output. So that's the idea. You take some observations of whatever the price of a house based on different features. I guess I'll keep using that example. You go through a bunch of observations, and then you have a new house which has these features, and you want to try to predict how much it'll sell for, or how much you should ask for in terms of the price. So let's take a simple example where we have only one feature and 4 observations. So our matrix A is this. This is our bias or intercept column, and then these are the observations for our one single feature that we have, and then these are the outputs for the given observation. So 1 corresponding to 2, 2 to 3, and so forth. So we can put it in table form here. These are the inputs, observation 1, 2, 3, and 4, and these are the outputs 2, 3, 4, 5, and 6. Okay, then we do the computations for the pseudo-inverse. So you recall we had to compute A transpose A, which is this, then A transpose B, which is this here. Then this gives us a set of 2 equations and 2 unknowns. I'll leave out the details, but when you go about solving it, you get this vector x, 1/2, 7/5, and I'm taking the transpose. It needs to be a column vector. Okay, let's continue on the next slide. Continuing with the problem, I brought over our solution from the previous slide. So this was our x0 and this is our x1, and now we can use this to predict other values based on our 4 observations. So our equation f of d equals x0 plus x1 times d, and we can plug these values in here. So we only have the one feature to work with. So let's try 4. Now remember we had a value for 4 of 6. That was one of the observations. So let's see how well our prediction does for that. We put in 4 here for D, and we get 6.1, so that's pretty close. We didn't have an observation for 5, but we can take an attempt at a prediction here. So we put in 5, and we get into this equation here, and we get 7.5. So as I said, we can use this predictively. I've given you a very simple example, but hopefully you get the general idea. We can also compute the residual and the norm of the residual. So the residual is ax minus b. Just x, putting in x here, and then multiplying times a, subtracting b, and we get this here. And then the norm of this is just taking each one of these squared and adding them together, and we get 0.2. Okay, so that's it. That's the last slide in this lesson and the last lesson in this playlist. Thanks for listening.